Welcome back to another lecture. So in this lecture, we will be talking about resonance structures. Anytime we're talking about resonance, that means that there is a bond, or like there is a positive charge, negative charge, or let's say double bond that keeps changing position. Okay, we have two terms that you need to be careful about them: localized versus delocalized. Localized means it's fixed; it cannot move. Okay, and because it cannot move, that system is going to be unstable. But delocalize anything that can spread the positive or negative charge over more than one element, it will make the system happy. In organic chemistry, always you will be dealing with structure that sometime like the charge is moving from one carbon to 2 or 3 carbons far from it, and that's gonna make it really stable. Okay, so let's see what we have here. Okay, it says delocalize the electron or delocalize charge. Okay, and if you're talking about the electron, you have a negative charge. If it says delocalize charge, it can be also positive. And in that case, we have technically we're dealing with lack of electron. And is there any way to distribute the positive charge by sharing a lone pair from neighbor atom or a pi bond? Yes, it's possible, and we're gonna go after them. So as you see, in first case, the allylic lone pair, we have lone pair shared with this electron, and that one it will move. Forgive me, that one it will move here, so we get lone pair, and on carbon, and that at the end it's going to be negative, or like the rest, like a positive charge got distributed through a pi bond, and or lone pair sharing oxygen lone pair with one carbon, or oxygen is taken to 2 electrons to itself on the last one position of the double bond keeps changing. Okay, I'm going to go through them one by one. Okay, first one, we have a negative charge sitting on a carbon, and that carbon is a neighbor to a double bond. Okay, in order to have resonance structure, we need to have a neighbor like a neighbor pi bond. And in that case, we can move maybe negative or positive charge. Okay, so let's write what we have. Okay, we have, okay. Welcome back to another lecture. In this lecture, I'm going to go through resonance structures, and I will be talking about localized versus delocalized terms. Whenever you're saying localized, that means electron or positive negative charge cannot move, it's fixed, and that's going to make the system unstable. But delocalized means you can move the positive charge or negative charge. And how do I move the positive or negative charge? And like you look to the neighbor. If your neighbor has a lone pair or has a pi bond, then it can share it with you or share it with that carbon, and we can actually spread the positive or negative charge over a couple of carbon atoms, and that's gonna make the system happy. Okay. We have a bunch of them. As you see, we have at least 5 different systems. I'm going to go through all of them one by one, and let's jump and start with the first one. So the first one, we have a negative charge close to the pi bond. Okay, negative charge close to a pi bond, or the second one, positive charge close to the pi bond, or double bond. Okay, so I'm going to draw what I'm dealing with. The first one, I have CH3. Next, the carbon, and here I have CH, and then we have a double bond, and that carbon attached to CH3, and here CH3. Okay, and what else? The one that has negative charge, okay, well, I'm going to put lone pair on it, okay, but still is not acted. In order to make it acted, I will add 1 hydrogen. Okay, now take that. Okay, take that lone pair and move it here. Share it with this carbon. I mean, share it with share it with this carbon. Okay, and then what will happen with the pi bond? The pi bond that I'm going to highlight, this pi bond, it will move to this carbon. Okay, so let's draw. Okay, whatever I said. So we're gonna get CH3. Okay, carbon attached to another carbon through a double bond. This carbon is gonna have a hydrogen. Okay, and then we will have a carbon attached to CH3, and then here CH3. Okay, but I'm gonna show a lone pair on this carbon. Okay, this is equal to, okay, this is gonna be equal to this structure. Okay, and okay, I got rid of the hydrogens and I tried to make it, easier. Next one. Okay, before I start the next one, look, I did not break any bond. The only thing I changed position of the pi bond. Pi bond, double bond used to be on the right side, now is on the left side. Okay, now is on the left side. How about the negative charge? Negative charge used to be there. Okay, used to be on the left side, now is on the right side. Okay, that's that one we call it resonance. We managed to create technically resonance structure, and the negative charge got distributed over here. Technically over, we started from here, 1, 2, 3 carbons, and that system is going to be super happy. Okay, next one, we have CH3. Okay, a carbon here, carbon with H, and then carbon, CH3. And CH3 here, and of course we have a double bond there. Okay, and now, okay, the carbon that I'm going to highlight, or the one that it has a positive charge, okay, is missing one hydrogen. You need to show that hydrogen on it. Okay, and so what will happen now? I'm going to take those 2 electrons, the pi bond, and I will share them here, or I will put them there. Okay, and that's going to leave me with a positive charge on this carbon. Okay, it's going to leave me with a positive charge on that carbon. Okay, but let's subtract this carbon, see what will happen to it. Okay, in that case, we're going to get CH3, carbon, H, and here we get a double bond. Then I get carbon attached to hydrogen, here carbon attached to CH3. And then CH3. Okay, but this carbon now is octet. Well, that one is missing one electron, and like it's going to have a positive charge technically, and so that carbon is going to have a positive charge, and here it will be a +1. So this is equal to carbon attached. Okay, two carbons. Where is the double bond? The double bond, we're going to put it here. Okay, where is the positive charge? The positive charge is there. Okay, so again, this is one was the starting. This is the secondary structures. Okay, and let me shrink size here just to make it more clear. The top one as well. Okay, so top one, we started from here. This is number 1, and that's number 2. Okay, we good? Okay, so one case, we have an either negative or positive charge. Neighbor with carbon, neighbor with a carbon. Look, position, place of, the positive or negative charge from the neighbor. You started here. This is the place that you have negative charge. On the second carbon, there is a pi bond. Okay, here you have a positive charge. On the second carbon, you have a pi bond. Okay, next. Okay, I don't see a negative charge. It looks there is no negative charge now, but I have oxygen. Remember, if you have a heteroatom like oxygen, nitrogen, phosphorus, or like a sulfur, you need to make them octet. If we were supposed to have hydrogen, they, like whoever wrote the question, he or she was supposed to add it. We have to add the hydrogen to heteroatoms. Okay. When I say heteroatom, I mean oxygen or nitrogen, other elements. Okay. So they did not add. What do I need to do? I'm going to add 6 electrons or 3 lone pairs to it. Let's check the formal charge. Okay, we're going to draw a circle around it. This one is going to give us 7 electrons inside circle. We made one bond. It will be 8. How about the formal charge? Oxygen in group 6, but I see 7 electrons around it, so it's -1. So the total charge is -1. And there is a pi bond. Okay. Okay, there is a pi bond neighbor to oxygen. Okay, I can get this. Let's share one of the lone pair from oxygen, and if we do it, oxygen is going to get a double bond with carbon. Okay. And what will happen to the double bond? Double bond will move here. Okay. And that's going to give us a lone pair on this carbon. Okay. Now, be careful about this carbon. That carbon, okay, was acted. How do I know it was acted? Remember, here they didn't show the hydrogen, but doesn't mean there is no hydrogen. Okay, for carbon, always we keep adding hydrogen until we make it acted. So that carbon, that means it has one hydrogen here. And if you check it now, I see carbon with 5 electrons around it, made 3 bonds, it will be 8. Carbon is a group 4, but I see 5 electrons around it, so it will be -1. So what happened with the negative charge? Okay, negative charge from oxygen moved to carbon. Okay, so now carbon has a negative charge. How about oxygen? Oxygen in group 6, I see 6 electrons around it, it will be 0. Which one of this is more stable, 1 or 2? Number 1. Okay, why number 1? Because negative charge is sitting on oxygen. Okay, next. Again, oxygen is supposed to be acted, so I'm going to put the 3 lone pairs on it. What's the formal charge for oxygen? Okay. Formal charge for oxygen. I go oxygen in group 6. I see 7 electrons around it, -1. Okay, so oxygen has -1 and carbon has +1 charge. When I add them, it will be equal to 0. Okay. Now, is it possible to share one of lone pair from oxygen with carbon? Yes. And if you do it, you get this structure. You get double bond. Okay, so one of the lone pair, it will be shared. Okay, like the previous time. Okay, we shared it with carbon. And so I'm going to share it with that carbon, and it will give me oxygen with 2 lone pairs. Now that carbon, it will be acted. Okay, and the rest, they will be untouched. Okay, now formal charge for this oxygen is 0. For carbon also, that carbon, the one I'm going to highlight, this carbon, the formal charge for it also is 0. So all are acted, and also formal charges are equal to 0. So that means this is going to be the best Lewis structure. And how about next one? Again, I have oxygen, a bridge, and like it got a bridge between 2, carbons. Okay, technically, we have two groups. We call them ethyls attached to oxygen, and this is an ether, but it has a positive charge. Oxygen is not acted. So what do I need to do with oxygen? I'm gonna add lone pair to oxygen. I will keep adding until I make it acted. So here you go. I have 2 lone pairs. Can I share one of these lone pair with this carbon? Yes, you can do it. And if you do it, okay, you're gonna get double bond there. Okay, so I get I'm gonna get this. I have oxygen here. I use one of the lone pairs, so I'm left with only one. And what will happen with that lone pair? I will show it here as a double bond. Okay, what do I have on this, carbon? Okay, that carbon, it used to be +1. Okay, and that carbon is missing 1 hydrogen. Okay, they need to, you need to add 1 hydrogen to it. Okay, so in order to keep it acted, I'm going to add 1 hydrogen here. It doesn't mean that we did not have it before. No, there was 1 hydrogen before. Okay, there was. They didn't show it. Why? Because we said for carbon, we don't show the hydrogen atoms. Okay, so Now, check the formal chart for oxygen. Oxygen is a group 6, but I see only 5 electrons around it, so oxygen is a +1. Okay, how about carbon? If you draw a circle around carbon, it will be 0. Okay, so the charge from oxygen from carbon moved to oxygen. Which one is more stable? Okay, which one is more stable? Okay, it's better. Okay, it's better to have all of them acted. Okay, also it's better to have all of them acted with 0 charges. In this case, I don't have option. Okay, and I will say both of them to some extent they will be unstable. Okay, for sure, both of them are unstable, but one on the right side is a bit more stable. Okay, it will make it more stable. And but again, the positive charge, majority of the positive charge will be located on carbon, not oxygen, because oxygen should not have a positive charge. Okay. Next, I have oxygen is not acted. Okay, so I'm going to add 2 lone pairs to it. Next. Okay, this carbon is acted, is happy. So what do I need to do? Is there any way to steal those 2 electrons and give them to oxygen? Okay, can I take those 2 and give them to oxygen? Yes, it's possible. So what we're going to do, we're going to steal those 2 electrons and we will give them to oxygen. Okay, and I will get this structure. I will get oxygen. Now, oxygen is going to get 3 lone pairs. Okay, how about this carbon? This carbon, we stole one, like technically 1 pi bond from it. So now that carbon, it will have a positive charge, and the carbon is a group 4. I see only 3 electrons around it. It will be +1. How about oxygen? Oxygen is a group 6. I see 7 electrons around it. It will be -1. And this is the proof for oxygen. Okay. So which one is more stable, 1 or 2? Okay. 1 or 2. Of course, 1 is more stable because all the formal charges are 0, 0. Okay. So the one I'm highlighting are the formal charges. Okay. In last structure, we have a pi bond. Okay. And so we have a triple, technically 3 pi bonds, and okay, that's a pi bond, and pi bond. This is equal to carbon attached to hydrogen, carbon attached to hydrogen, carbon attached to hydrogen. Okay, now in order to make it acted, I'm going to put double bond here, next double bond there, and the third double bond, it will be here. Okay, can I change position of the double bond? Yes, you can draw the bond, you can put the double bond somewhere here, and then this one, it will go there, and this one, it will go here. So we're going to get pi bond here, and then I can move this pi bond here and do the same rotation with the rest. And if I do it, I get pi bond here, there, and there. So I got 3 Lewis structures for benzene molecule. So we call this one benzene molecule, and it's aromatic and smell good. But in organic chemistry, if you smell like an aromatic compound, and try to be far from it, because they are really dangerous chemical compound. Long term, they are capable of technically creating cancer in our body, unfortunately. Okay, thank you very much, and I'm gonna stop here, and I will continue resonance structures in the next video. Take care.